expect in this lesson today? The expectations are as follows. I will explain how current is related to the magnetic field, and then the electromagnetic induction and the basic principles behind that process. Also, I will describe and demonstrate Faraday's law. Also, I'll explain and apply Lenz's law. I will also explore and apply the factors that determine electromagnetic induction. So sit back and enjoy. So in the next slide, I present a simple simulation. Now, in this simple simulation, you realize that there is a reservoir of water. Water is made to pile up until a certain level is attained. That means the water accumulates potential energy. And then when the gate is opened, this potential energy is converted to kinetic energy, and water flows down the channel into the chamber of the turbines. In the turbines, water is allowed to accumulate as it moves around in the turbines. By so doing, then we have the turbines moving. The turbine cannot move unless we have the downward gate open. Now, when the downward gate is open, we have the kinetic energy of water turning the turbines. Now, this kinetic energy is transformed into mechanical energy. The mechanical energy in turn causes electrical energy to cause electricity to be transmitted to the national grid system. Of course, there are other processes that this voltage undergoes before it is fed into the national grid system. Now, basing on that, we've seen that energy transformation taking different forms: potential energy, kinetic energy, mechanical energy, and electrical energy. Now, to understand what is happening between the turbine and the power station, whereby this electricity or a power is converted into other form so that it is fed into the national grid system, it is good that we discuss the simple circuit that is always discussed in Form 1. Now, here is a representation of the basic circuit for part A, where we have a battery, we have a switch, the light, and the wire. Now, for part A, the switch is closed. A symbolic representation of the same in part B represents a circuit that is open. And so, we have a battery represented by long bar and short bar. The long bar and short bar in electronics have a meaning. The long bar is positive, the short bar is negative. And so, in this case, when one is asked to indicate the direction of flow of the charge or flow of electric current, the first thing one needs to do is to close the switch. Once the switch is closed, then current is made to flow. And the current flows as indicated here. Current will flow from the negative terminal of the battery to the positive terminal of the battery. Now, what happens to the charge? The charge deflects from the positive terminal to the negative terminal. And so, to understand all this, it is good that we have a simulation to represent the phenomena. So in this case, we have a circuit that is modeled. There are two circuits here. One is using a dry cell, and the other one is using an alternating current. So a dry cell represents a direct current, and then the other one having the symbol plus and minus represents a current that is fluctuating after a short while. Now, in this simulation, I will present direction of flow of the charge and direction of flow of current and the effect of the type of current on each. So we close the switch. In the first circuit, we see that the bulb lights continuously. Now, what happens if I close the switch in the second circuit? The bulb lights, but in this case, after a short while, the bulb goes off and then again turns on. So what is happening here? It is because we are having current moving in the clockwise direction. After a short while, the current switches again in the opposite direction. Now, how do we represent current flow? So this is the deflection of the charge. Current flows in the clockwise direction in the first circuit, and in the second circuit, we have current moving in the clockwise direction, then after a short while, it changes direction. And that's why we have the bulb turning on and off, turning on and off. So what is the direction of flow of the charge? The charge in both circuits will behave as shown. In the first circuit, the charge deflects anti-clockwise in the conductor. And then in the second circuit, we have the charge deflecting clockwise and anti-clockwise momentarily, and so thus varying the behavior of the bulb lighting. So why is this important? It is because with this flow of current, we are able to predict magnetic field around a conductor. Now, here, if I single out the conductor labeled part A, and then I analyze the magnetic field around it, this magnetic field cannot just anyhow be predicted. There is a rule that must be followed. So what is this rule? This rule is studied in Form 2, the 844 curriculum, whereby we have the right hand is held in such a way that the thumb points to the direction of flow of electric current, and then the four fingers encircling the conductor point to the direction of flow of magnetic field. And so if I take this pen here as an example of a conductor that is straight, then we have current moving, exiting through the teeth. So I'll grasp it this way. And so this becomes perfect right hand grip rule. So the magnetic field is a set of concentric pattern around the conductor. So what if the conductor A is not straight? If that conductor is not straight, then we need again to have another rule to predict the polarities of the coil. Now, there are a number of rules that can be used, but in this case, I advise students to focus on one rule, which is called the clock rule. So the clock rule states that when one views at one end of the coil and current happens to flow in the clockwise direction this way, then there is magnetic field that is set up to cause this face to be the south. Otherwise, if current flows counterclockwise, then this end becomes the north. Now, as seen on the diagram, it is clearly labeled when current is moving clockwise, there is the south. And then on the opposite side of the coil, we have the north. A similar situation is encountered in the second part of the diagram, where the direction of current reverses and the corresponding polarities are labeled. Now, with that, then the basic bar magnet that I introduced in the beginning, we analyze it in detail. A magnet has magnetic field lines around it. So, as seen in part B, we have the field lines running from the north to the south. Now, in this case, these magnetic field lines represent a path along which the magnetic energy flow. So we need to use this energy to do something, as I am going to discuss in the next slides. So in this case, it is good that we simulate the magnetic field. We simulate the magnetic field around a bar magnet. And so, in this case, what I see is there is a magnet and labeled north and south. So here we are going to do a number of activities. In our syllabus, we are informed that ion filings can be used. So in this case, ion filings used, we are going to use submagnets, which have the north and the south. And so inside a magnet, there are submagnets that have the south. In this case, they are labeled south and the north. And so if we put this bar magnet inside a field, then the magnet will behave in this way. The submagnets having the north will point to the south of the bar magnet, and the south will point to the north of the bar magnets. So by so doing, we can see that there is a set of concentric, a set of pattern that the submagnets align around the bar magnet. So if we use a compass, it can tell us or prove to us the true polarities of the bar magnet. So in this case, the compass has a pointer that has the south and the north. So if I flip the bar magnet, then the point of the compass also flips to indicate that we have the like poles repelling and unlike poles attracting. So in that case, then we are ready to move to the next slide. Now, we have just talked about magnetic field lines and how they propagate energy through themselves. All right, so the magnetic field lines carry magnetic energy along with them. And so we have in a way that when this field is directed onto a surface at an angle of 90, then the energy are directly induced into the surface. Now, when these magnetic field lines are slightly inclined to the surface at an angle less than 90 degrees, then we have less energy induced into the surface. Now, what happens if the surface is parallel to the magnetic field? A surface parallel to the magnetic field means that little energy is induced into it. And so, having conceptualized all these properties of magnetic field lines here, then the next presentation, we discuss the effect of induced energy into the charges in the surface. Now, electromagnetic induction, this is a process. So how does this process take place? So in this case, if one holds a bar magnet like this, and this is the coil, and the bar magnet is made to move into the coil, the bar magnet is displaced over a distance like that. And so if the bar magnet rests inside the coil, then we have the energy not being induced into the surface of the coil. Now, if that happens, then nothing is induced. There is no energy induced into the coil. So that means we cannot have current flowing. Now let me just take you a step back. We have the bar magnet here. A force is applied into the bar magnet to displace into the coil. So assuming we have a force of 20 Newton being applied to move the bar magnet into the coil over a distance of, let's say, 50 centimeter. Now we have to convert the 50 centimeter into meters. So 50 centimeters, convert it into meters is 0.5 meter. So multiplied by the force, which is 20 Newton. So 0.5 multiplied by 20 is the same as 5 multiplied by 2. We get 10 joule. So by so doing, we are transferring 10 joules through the magnetic field lines into the surface of the coil. Now, the surface of the coil has the charges. So these 10 joules encounters the charges in the surface. Now, when these charges receive the 10 joule, they move or displace. By so displacing, then current is made to flow. And so, to give a simple definition of what electromagnetic induction is, it is good to understand what an EMF is. So, the transfer of energy per unit charge to an electric circuit is what is called electromagnetic force. And then, now that we have a bar magnet with the magnetic fields varying from one point to the other, then we have the charge displacing. And whenever we have a charge displacing, current is also made to flow. So, in this case, I take you to the lab where Faraday conducted the experiment. And so here we have a bulb, and then we have a coil. This coil is connected to a circuit that leads to the bulb, and there is a bar magnet. So with this bar magnet, I'll have to show the magnetic field lines, because if I displace the bar magnet the way it is, we only see the effect of the displacement, that is the bulb lighting. But we do not know what is happening in between. So if I turn on the magnetic field lines, so these field lines carry energy with them. So when the bar magnet is displaced into the coil, the energy is transferred into the coil through the process that is called induction. And in that process, we have the energy causing charges in the coil to displace. And they do not only displace in anyhow, they displace in a manner that they set up electric current to flow in a specific direction. So the same way, when we displace the bar magnet outside that way, we also observe that current is made to flow. Now, why does current flow? It is because the displaced charge flow back to occupy the original position. And so, if we increase the rate of displacement of the bar magnet, we also see the effect that the brightness of the bulb increases. Now, at this point, we also need to determine the magnitude of the voltage. So, if we have the voltmeter in place, we see that anytime we move the magnet into the coil, the pointer deflects momentarily depending on the direction of displacement of the bar magnet. Now, at that point, we are seeing the pointer of the voltmeter deflecting to the left and the right sorry, it is not a voltmeter, it is a galvanometer because it has the positive and the negative. That means current can either move clockwise or anti-clockwise from the central point. Now, a galvanometer is an instrument that is used to measure the voltage of an induced current. Now, in this case, if we increase the number of coils, then this number of coils must also have effect. So we have been using a coil that has got many turns. Now I want to increase the number of coils such that when the magnet is moved in and out of these coils, it causes the magnetic flux to link in both. And in so doing, the size of induced EMF increases, which in turn increases the size of induced current. And so the same case happens. Now, after the simulation, we go back to the presentation. Now, what has been happening is induction. But now, how do we explain this induction as per what has happened in the lab? So here we have part A, B, and C. For part A, we have the bar magnet moving into the coil this way. Now, when the bar magnet with its north pole moving into the coil, the energy, mechanical energy, is induced into the coil in such a way that it displaces the charge to move counterclockwise. When the charge moves counterclockwise, we have the current moving clockwise. Charge moves counterclockwise, the current moves clockwise. Now, in this case, the displacement of the charge takes place in such a way that it sets up a current to flow in the anticlockwise direction. So the charge moves clockwise. The flow of current in the anticlockwise direction causes this face of the coil to acquire a north pole. And so, as one moves the bar magnet into this end, resists that magnet from entering the coil. Now, when the bar magnet is made to rest into the coil, there is no induction of mechanical energy into the coil, and so no charge flows. That means no current is induced in the coil. Now, when one draws out the bar magnet, the face of the coil adjusts itself in such a way that the charges displace counterclockwise, causing current to flow in the clockwise direction. That flow of current in the clockwise direction causes this face of the coil to acquire the south, such that when the bar magnet is moved out, the south attracts that bar magnet. And so, in the process of having current flowing clockwise or in the clockwise or counterclockwise direction, we have the pointer of the galvanometer deflecting in the same direction of flow of electric current. Now, for part A, the charges deflect in that direction, and then current flow in that direction. And so the pointer also moves in the direction of the current. For part B, there is no induced energy into the coil, so the pointer rests at 0. For part C, we have the bar magnet, cylindrical magnet, being pulled out of the coil. And so this face adjusts itself to attain or acquire the south polarity, which resists the cylindrical magnet from being pulled away. And so charges displace anticlockwise, current flow clockwise, such that we have current in the circuit moving that way, in that direction. And so does the pointer deflect to the left of the center. Now, what does Faraday law state, basing on the explanation that we've just done. So Faraday's law observed this, looking into details the effect the magnetic field which carries energy has on the coil. And so Michael Faraday formulated a law which must always be used, and it has always been used in the manufacture of generators or any gadget that produces current due to motion or depending on the displacement of magnetic flux on the surface of a coil with the time. And so it was put as follows: the rate of change of magnetic flux linkage is directly proportional to the induced EMF. Now, someone somewhere observed this keenly and came up with another law. So this physicist is called Lenz. And so the law is called, named after him, Lenz's law. Now, the current that is caused to move, let's see here. The current that is caused to move clockwise, it sets up a field on this face that tries to resist the polarity that comes into the coil. And if it has to move out, that polarity must adjust itself on the surface so that it resists the cylindrical magnet or the bar magnet being pulled out of the coil. Now, how does a student know this? In somewhere, I discussed the clock rule. Now, once you know that a bar magnet with the north is entering into the coil, then the current will be caused to flow. It is good you realize that the charges will deflect in a manner that a current flows to cause what? To cause a polarity at this end that resists the bar magnet moving into the coil. And so when current flows clockwise, we use the clock rule to predict the polarity of this phase. So if one views the end of the coil and current flows in the clockwise direction, that end is the south. Otherwise, if anti-clockwise, it is the north. Now, to illustrate that, then it is good we simulate Lenz's law. So, at that point, we see a magnet moving into the coil, and the current displaces anti-clockwise. So that phase becomes the north. When it becomes the north, it resists the magnetic flux moving on the surface. And then, when the bar magnet moves out, that phase adjusts itself in a manner that current is made to flow in the clockwise direction to resist the bar magnet pulling out of the coil. The bar magnet pulling out of the coil. Now, as we've been discussing, you find that there are factors that determine the size of induced EMF. Now, how do we discuss these factors? I will discuss each of the factors one by one in the lab. So here we have a bar magnet that is facing a coil. So I want to move this bar magnet into the coil and see the effect. So we have, when the bar magnet is made to move into the coil, we see the charges displacing. So in either direction of displacement of the bar magnet, we have the charges displacing. And so if I displace the bar magnet from the right hand side into the coil, the charges displace anti-clockwise. And so we have the current moving in the clockwise direction to set up a polarity which is opposite to the end of the bar magnet facing the coil. And so by the displacement of the charge, current is made to flow. So that is, if you move it a bit faster, current is made to flow. Now, what is happening here? We have the magnetic flux linking to the coil, and the rate at which they move on the surface of the coil, there is induced energy. The mechanical energy is transferred into the coil, and by so doing, the charges displaced to cause that current to flow. So we can have a voltmeter, a galvanometer connected to the switch, to the coil, so that we have, we make observation of what the voltage it produces when the speed of motion of the bar magnet is increased. Now, that is one, the speed of magnetic, the speed of motion of the bar magnet. That's the rate of change of magnetic flux linkage. Now, what happens if we increase the strength of the magnet? What happens to the size of induced EMF? So we have that way, and so it shows that when the strength of a magnet increases, also the size of induced EMF increases. Now let's have this bar magnet moving in a field, and then let's also have a compass put in place, and let's move the bar magnet once again, and one can see that the pointer of the galvanometer displaces with a wider margin. And so what happens if we increase the number of turns of the coil? So we are using 2 coils. Now I increase to 3 turns. So we move the bar magnet into again. So increasing the number of turns of the coil means that we make more charges available to interact with the induced electromotive force. And so the more the charge displays, the more the current is induced in the coil. Also, the plotting or the compass helps us to show the direction of motion of the bar magnet. If I happen to displace this magnet to the other end, then the compass pointer adjusts its position in a manner that it faces the pole opposite to itself. Now, with that, then we can move to an electromagnet. So this is an application. We have a direct source of current as discussed in the second slide. Direct source of current is indicated by a dry cell. So this dry cell is at higher potential, and so it causes charges to move around the coil. When these charges move around the coil, current is also made to move. So this is the positive part of the battery, and this is the negative part of the battery. So we can also increase the number of loops so that we have 2 instead of 1. And so in that case, if turn on the charges to move, they move in that direction shown. and so current is moving opposite to it. All right, current is moving opposite to it. So we had a technical glitch. So just a moment, we switch to the app that I'm using to simulate the circuit. All right, so we are discussing the strength of a magnet and its effect on the induced EMF. We have also discussed the number of turns in the coil and how they affect the size of induced EMF. Now, sometimes we have a soft magnetic material placed inside the coil. Now, this material has an effect. So what is the effect? The effect is that when the bar magnet is made to move into the coil, not all the magnetic filaments link to the coil. They move astray, some of them. And so to ensure total linking of magnetic flux into the coil, then we use a soft magnetic material. This can be an iron rod, which concentrates magnetic field inside the coil. And now that the technician has worked on the system and it's working, we switch back to the explanation. So in this case, we have charges moving clockwise. And so the current is displacing anti-clockwise. The current is displacing anti-clockwise. Now, in that case, what's the effect of an AC current? The AC current displaces the charge sinusoidally after a short while in the clockwise direction, after a short while in the anti-clockwise direction. Now, when we increase the number of loops, in this case, we use 4. Then, these 4 loops make more charges available. And so, we investigate the effect of this on induction. So, this is how the field fluctuates around the coil. At one point, we have the sub-magnets pointing into the coil. At another time, we have sub-magnets pointing away from the coil, depending on the polarity that is set up at one end of the coil. So if we have to use a compass, the compass behaves the same way the magnetic field is fluctuating around the coil. Now, if we show the meter, we can be able to see how the size of magnetic filaments is fluctuating in both axes X and Y direction, which is causing current to flow, so that we have a sine curve indicated on the display like that. Now, the application of this is in the transformer, whereby we have a current flowing in one coil induces an electromotive force in another coil. And in that case, we have the second coil causing an electromotive force to flow. So the application is demonstrated as follows. So we have the initial battery connected to a loop. And so we have to cause the charges to flow. So in this case, the charges are flowing directly in the clockwise direction. Now, when I put this first coil into the second one, there is no direct connection between the two. But the change of magnetic flux in the first one induces an EMF in the second coil. So this second coil is called the secondary coil. The first one is called the primary coil. And so we can enjoy the effect. So if I displace the primary coil into the secondary coil and stop it there, no effect is felt or observed. But if I displace the primary coil in that manner, we have current induced in the secondary coil. Now, what if we are applying this one for commercial purposes? We can't have somebody there displacing the secondary coil now and then. We need an automated system that keeps displacing so that we have an EMF induced in the secondary coil, and so the need for an AC current. So with the source of AC current, if I move the primary coil into the secondary coil, the effect can be seen. So we have, every time the current changes direction, the effect is observed on the bulb, whereby the bulb appears flicking like that. It is because the current is changing direction. Now, what is the effect of increasing the cross-section area? The cross-section area of the coil. Let's see. And then also we increase the number of loops. Now the size of the light produced by the bulb also increases. And so in that case, then this tells us that the number of loops also increases the size of induced EMF. So when we have a compass put in place, we have the pointer of the compass oscillates at a rate which the charge in the coil is oscillating. Now, it's not about the charge, it's the effect of the charge. So the current flows, causing a field. So the field is the one responsible for oscillating the pointer of the compass in the manner shown. Now, how is this one applied if we increase, if the number of loops is increased? We've seen the effect. We have also seen the effect of increasing the cross-section area of the coil. Now, let's have the galvanometer placed in position and see the effect of each factor. So I'll reduce the number of loops. When the number of loops reduce, also the size of induced EMF reduces. What about the cross-section area? When the cross-section area reduces, also we have the size of induced EMF reducing. Now, the application of this is based or is in the hydro dam, where electricity is produced because of the moving waters, as illustrated in the hydro dam that was in the beginning. Now, in this case, I will turn on the tap to make that bar magnet placed on a rotating coil to keep moving. And at every time the bar magnet changes its poles facing into the coil, we have an EMF induced, which induces a current. So what about if we increase the speed? The speed means that we have more water moving. And so the faster the coil moves, the more the induced current is. And so what happens if we increase the strength of the magnet? When the magnet strength increases, we also have EMF size increasing, evidenced by the magnitude of the brightness of the bulb. Now, what happens to the effect of increasing the area of the surface? It also increases the magnitude of induced current. So, what about if we use a galvanometer. Then increase the number of loops. There is also increase in EMF. Now, in this presentation, we have discussed quite a number of concepts. Remember, the important ones is direction of flow of charge, direction of flow of current. Also, we have the clock rule, Lenz's law, and Faraday's law. Now, in this conclusion, I would like you to attempt these questions. Name the instrument used to measure the current in Faraday's experiment. Examine yourself. It is a galvanometer. 2. Explain how the nature of the core affects electromagnetic induction. Magnetic field is concentrated into the coil. This affects the increase in the size of EMF induced. Now, as we come to the end of the presentation today, I would like to acknowledge Mangu High School fraternity for their support, the University of Colorado for designing the app for the simulations, and then the KUTV and our esteemed viewers. Our lesson is ended. Thank you.